Yes, I have. I have some explaining to do. So before we get to probability and counting principle, I want to take a moment and go back to probability from yesterday when we were towards the end of the hour and started talking about what happens when given comes up. Because we'd spoken about how you could just look at the chart. And I'm like, I'd done so long that I just looked at the chart, grabbed the information, and did it, that we hadn't done it mathematically. When I did it mathematically, we were getting a different answer. I went back and looked as soon as your guys' class was over. I'm like, wait a minute. Executive given a Republican would be an executive Republican. It'd be 34 out of 55. So I'm like, why when I did it with using the formula was I getting something different? That's weird. Here's why. You'll notice just up above there where my little frowny-faced guy is, that somebody, me, had put that the formula was the probability of A and B divided by the probability of A. Well, that's why I wasn't getting the same answer, because it's divided by the probability of B, not the probability of A. So you'll notice if I use the right formula, even though I still like just looking it up in the table, it's easier, but I'll explain that on the second one. If you take the probability of A and B, an executive Republican, okay, it'd be 34 out of the total number of people in my chart, 140. Okay, that's where this is coming from. Divided by the probability of B, divided by the probability of being a Republican, 55 Republicans out of 140. Of course, when we divide by a fraction, we flip that fraction, which is going to make the 140s go away, and I get 34 out of 55, which is the correct answer. But again, I don't think you need to go through all of that when you're doing this. If it says independent given a production worker, I go to where the production workers are, I find my independent, which is 8, given that it's a production worker just tells me what the denominator is. The given value will always be my denominator, and then just find within that row or column where your particular value is. In this case, the independent would make it 8 out of 92 and then reduce it still. So I do apologize that I got those flipped, but like I said, forever I've just been looking at the chart, finding the given row or column, and then finding what I want and not using a lot of the formula. So trying to get mathematically fancy kicks me in the butt. So when you run into that, typically in the future, I'm just going to use the chart anyway. However, that's going to kind of lead us into some things for today. Probability and the counting principle. The fundamental counting principle is a wonderful thing. It allows us to keep life simple without a bunch of formulas. And basically it comes from the probability of these two different types of things, independent or dependent events. Independent events, one outcome doesn't affect the other. I just multiply their two probabilities together. For instance, rolling a number on a die and then rolling another die. My second die doesn't look at the first die and go, ooh, you rolled a 3, I can't do that now. It's totally separate things. However, if you have a dependent event where your second event can be affected by the first one, we'll still multiply them together, but we'll take them in order. So for instance, without replacement, if you're dealing with a card, if I pull one card out and keep it out of the deck, now I have one less card to work with. That changes the probability of things. So that's one thing that we're going to talk about a little more in depth today. But the other one's the fundamental counting principle, which is lovely. Because basically we just look at the opportunity to put things in order, how many choices we have for each, and just multiply them together. The one thing I'll make special note of, when we're dealing with factorial, which we were a little bit yesterday with permutations and combinations, if you get a 0 factorial, which can happen, that value is going to be 1 by definition. So it'd just be like dividing by 1. So here's how this works. An easier day 2. We have a lunch special today. You can choose 1 out of 3 entrees, 1 out of 3 side dishes, and 1 out of 4 drinks. How many different meal choices are there? Basically, you've got 3 entrees, you've got 3 side dishes, and you have 4 drinks, and you're just going to multiply the number of options together. Okay? Notice it says how many different meal choices, not what's the probability of something occurring, because probability will always be a fraction. If you're just asked for choices or options, you don't need that. Okay, so it wouldn't be 1 out of 36, it'd just be 36. Bless you. And that's the same thing with any of these. Make your own adventure story. 6 starting points, 4 plot choices, 5 possible endings. How many adventures? Multiply them together. Get an answer. Now, are they always going to be quite that straightforward? Well, no. Sometimes you're going to have to do a little bit of thinking. For instance, 3, it changes a little. A password is 4 letters followed by 1 digit. Upper and lowercase letters may be used and are considered different. How many passwords are there? So I'm going to have 4 letters and 1 digit. If upper and lowercase letters are different, how many options do I have? 52. Because I have 26 upper and 26 lower. Is there any mention anywhere that I can't repeat letters? No. So if they don't give me that restriction, I'm not going to use it. I'm just going to keep using. So if I want to do A, I can. Followed by 1 digit. Ooh, this is always fun. How many digits are there?
10.
10. Dang, nobody got sucked into saying 9. And then you just multiply those together and see how ridiculously large many number of passwords there would be.
Yikes.
So try hacking that. Okay. Somebody probably can though. So
But they just get lucky the first try.
they could get lucky the first try. It's true. Not very likely, but possible.
Oh.
How many ways can you listen to 3 songs from a CD that has 12 selections? Now again, this is where I could get into permutations and combinations, but again, why when you can keep it simple? If I'm listening to how many choices do I have for the first song I listen to? Okay, so once I listen to that song, we're assuming I'm not listening to the same song again here. How many options would I have for the next one? 11 and 10. That's the fundamental counting principle. Once I choose one, my number of options goes down 1 each time until I've hit the number of selections that I want. But that's the same with any of these. Members from 6 school organizations decorated floats for the parade. How many ways can first, second, and third be awarded? Well, there's 6 teams that could get first. And then once we have the first place winner, and we go to pick second, now there's only 5 choices because you can't get first and second. At least I hope not. And then there'd only be 4 teams left possibly that could get third. And multiply them together. And the same thing here on this last one. Jamie purchased 3 blouses, 3 jackets, 2 skirts. How many different outfits using a blouse, a jacket, and a skirt are possible? Just multiply the options together. And get my answer. Okay. Now, one thing I want to mention on this, down at the bottom, because sometimes this drives people nuts. They're like, why are you using capital P instead of the lower p? Because it's not page 10 and 11. There's a section at the start of your book that's like a preview, like a 0 chapter. That's where this assignment is. So if you go to regular page 10, you are not going to find anything that looks like this. So in that front part of the book, look for the capital P's in that 0 unit, and that's where you are going to locate. Actually, we'll pop it up here on the screen so we do not have confusion. So at the front of your book, notice it actually has a P on the 10 there. It's chapter 0. That's where all this stuff is going to be. So this first part of what we're doing today is basically going to be some stuff with counting principle on P10 and P11, 1 through 16. That's going to get us started on to homework check 15 because, well, homework check 14 is tomorrow. So it kind of gets us started with that. Now, I'm not going to do every single one back here But this is just getting us a little more info. We're note heavy for these first 2 days, and then it goes like clear sailing for about 3. So just a couple of definitional things, and we'll get you into things here. Exploring probability. Okay, experimental probability is when I actually do the testing or spinning or practicing or whatever other word it is you may want to use. You're actually performing the act. You're not just assuming what should happen. Like when you roll a die, you assume each number should come up 1 of 6 times. If you actually roll it and see what happens, that would be experimental. Whereas theoretical just is what should happen. So like for instance, we all know the theoretical probability when you flip a coin. Probability of getting heads would be 1 out of 2. Because you get heads or you get tails. But what if I actually did some experimenting? What if I actually flipped a coin 10 times and got 3 heads and 7 tails? If I were to ask you the same question, what's the probability of getting heads experimentally? In this case, it'd be 3 out of 10. So you have to be careful and see what the word that's being asked for would be as I'm doing this. I'm just going to get down to here, and then we're going to kind of be out of the way with this one, because I just want to kind of get you a feel for some of this. Okay, suppose this spinner was spun 60 times and stopped at the number 4 on the dial 14 times. What's the experimental probability that the pointer will stop at 4? Well, if I actually did it, it'd be 14 out of 60. Or I always like to reduce my fractions. But is that the same as theoretical? No. If I spun it 60 times, how many times should it stop on the 4?
6 out of 4. 1 out of 5 if you want to simplify it, but 6 out of 4.
Okay, 1 out of 5 if I wanted to simplify it, because you're right, there's 5 slots. But it would be 12 out of 60 if we were going on theoretical. So again, it's kind of rare that experimental and theoretical will come out exactly the same. And then for any spin, what's the theoretical probability that the spinner will stop on an odd number? Okay, 3, 1, 3, or 5 out of 5 total. And then I could extrapolate that to any number of times that I wanted to, if I really wanted to or needed to be able to do that. And then finally, suppose the number 3 came up 42 times in 60 spins. Would you conclude that something was wrong with the spinning mechanism? C, okay. Why?
It's far over the odds.
Yeah, how many times should it be showing up? Yeah. Should only happen 12 times. But that's the type of thing we're talking about with experimental versus theoretical. Theoretical, what should happen. Experimental, what actually is. And like I said, I don't want to go into overkill with you guys on this. So I will go away from this for a moment, if that is okay. They're like, sure. Okay. So the last thing today, and here's going to be one of our infamous note/assignments. It's the assignment sheet, but I'm going to do some of it with you because odds gets to be an interesting little thing. Probability and odds, very closely related except for a couple of very minor differences. Probability is favorable outcomes out of the total number. Odds is favorable outcomes out of unfavorable. They take some of the same values into consideration, but just use them differently. And normally with odds, we use a colon instead of a fraction just so we can visually see, oh, it's a colon, it's odds. Oh, it's a fraction, it's probability. So again, probability we don't have to worry about as much because we've done it a whole lot. But here's what we'll do. This top part, again, probability of getting a 2. Okay, 1 out of 6. Harty, you bore me with all this stuff you do. A number less than 4. Okay, so 3, 2, or 1 would be 3 out of 6, or 1/2. You're like, yeah. Again, word usage. A number 2 or greater, what would be the theoretical probability of that? 5 out of 6, because I'm going to include the number 2. A number greater than 5 would only be 6. It'd be 1/6, and I'm set with that. However, when I go to odds, remember, now it's favorable. A multiple of 2. 2, 4, or 6, there's 3 of them. How many numbers on the die are not a multiple of 2? 3. 1, 3, and 5. That becomes the other part of my ratio. And just like fractions, we like to reduce them. So basically, 1-to-1 odds tell me it's like a coin flip. I have an equal chance of what I want to occur happening as I do for it to not happen. A number greater than 2. 4 instances. How many numbers on a die are not greater than 2? 2. And reduce it. An even number actually is the same thing as the multiple of 2. It's the exact same number, so I'm not going to talk about that too much. A number less than 3. 2 or 1. There'd be 2 of those. Those are my successes or my favorable outcomes. The other 4 numbers, 3, 4, 5, and 6, that don't go with this would be there, and basically just switch the odds around the other way. And yes, here come the blasted cards again. I need to just permanently put them up over on that board over there, just in case we need them here. So my card people can kind of help us out here. All right. Probability of selecting a spade. I hear some of you half whispering going, I think it's 13. Yeah, because when we're talking about suits, okay, spades, hearts, diamonds, clubs, there's 13 of each. And I can always, when I can reduce that down, I should. If you want to go straight to the 1/4, you can. Probability of selecting a red jack. Jack of hearts. Jack of diamonds, 2 out of 52. Or 1 out of 26. Oh, here come the odds. Odds of selecting a heart. How many hearts are there? 13. How many non-hearts are there? 39. That's the part you've got to watch for. Because once that word in the middle changes from probability to odds, the way we calculate completely changes with it. Odds of getting a black 6. How many black 6s are there? 2. How many non-black 6s are there? I spit it out. 50. So again, we don't want to go into overkill with some of this, but we do want to think about it a little. I want to do one more on this side, and there's just a couple on the other side, and I will let you loose here. Number 15. What are the odds of, that should say, selecting a black card or an 8? Now this gets interesting. This is the one situation where I would actually start with fractions because it's easier to see what you're doing. So, okay, odds of getting a black card. 26 black cards, 26 non-black cards. So that takes care of my first part. What are my odds of getting an 8? 4 8s, one of each suit. 48 are not 8s. Some of you may have been thinking ahead to what I'm about to ask. But remember, if there's overlap, is there such thing as a black 8? And there's 2 of those, and there's 50 that aren't. So here is where I would say, I'd be like, okay, 26 out of 26, that's 1. I'm not even going to mess with it. And I basically at this point would say, okay, I want to keep life real simple on myself. Oops. Parenthesis lost, parenthesis lost. That's better. Make sure we're right, okay. So my odds would be 313 to 300. Now, if you left that as a fraction, I wouldn't mark it wrong. Again, it's just a way that we signify odds more often is going to be with the colon instead. Last twist I can throw at you. I only got one more. Oh, put it in a sentence form. So, let's say, let's look at 27 and 24 here, just to get you a kickstart. If the probability that an event will occur is 3 to 7, so again, will occur is 3. That 7, since its probability, is the total number of occurrences. What are the odds that the event will occur? Well, my success would be 3. How many non-successes would I have? 4, because there's 7 total, 3 are successful, 4 wouldn't be. 3 to 4. So you take the information, you kind of dig a little, and you come out with what you're looking for. Ooh, now we'll start with odds. If the odds that an event does not occur are 5 to 7, so not is 5, yes occur would be 7. What's the probability that the event does occur? 7 out of 12. 7 occurrences. That's my good events now. And 5 not and 7 occur means there's 12 total options, and that's where the 12 would come from. Okay. So just to kind of recap, when we're looking for possible range values for probability, probability is always a fraction between 0 and 1 because 1 would be 100%. It can't be greater than that. Odds are a different ball game. Odds can get humongous, especially like if you're talking about the lottery or something like that. You can get into millions and billions, and if you'd heard anything about when they had the NCAA tournament and said if you got a perfect bracket, they couldn't even really say the number in the correct way. There were so many zeros going along with it. So your job is to finish off this sheet and then deal with that P10, P11 book assignment to kind of put those together. And like I said, for the next couple of days, there won't be physical lessons. There's just going to be some different stuff applying these things that are going on are going to be assignments.